In the silent theater of our solar system, there are giants, worlds so vast, they defy our sense of scale. So alien, they challenge our understanding of what a planet can be. They are the gas giants: Jupiter, Saturn, Uranus, and Neptune. They possess no solid ground to stand on, no surface to land a ship. They are worlds made of storm, pressure, and mystery. We have observed them from afar, mesmerized by their swirling bands and hypnotic storms. But what lies beneath those clouds? What unimaginable forces reign in their deep interiors? Tonight, we undertake a journey that is physically impossible, yet scientifically vital. We will simulate a descent, a one-way plunge into the belly of the beast. This is your guided fall into the heart of a gas giant. Prepare to witness an environment where pressure can crush atoms and temperatures rival the surface of the sun. Prepare to fall forever. We begin. Your fall begins in silence. One moment, you are in the cold, hard vacuum of space. The next, you have crossed an invisible threshold. There is no fanfare, no fiery entry like you would experience on Earth or Mars. You have just entered the exosphere, the impossibly tenuous upper layer of Jupiter's atmosphere. You are approximately 3,000 kilometers, or nearly 2,000 miles, above the cloud tops that we see from Earth. Down here, the word atmosphere is a generous one. The wisps of hydrogen and helium are so spread out that individual atoms can travel for hundreds of kilometers without bumping into another. It's a ghost of a gas, a trillion times less dense than the air you are breathing right now. You are falling, and you are falling fast, pulled by the relentless gravity of a world that contains more than twice the mass of all other planets in the solar system combined. Your speed climbs to a staggering 180,000 kilometers per hour, or 50 kilometers every single second. At this velocity, you could cross North America in under 2 minutes, yet you feel nothing. There is no wind, no friction, no sensation of movement. You are in a state of perfect freefall, an object plummeting through a near-perfect vacuum. Looking down, Jupiter does not look like a planet. It is a place. It fills your entire view, a colossal wall of cream and amber stretching to infinity in every direction. The familiar bands of clouds are not quaint stripes. They are continent-sized rivers of weather, and you are falling toward them with unimaginable speed. Looking up, the sun is a brilliant, shrunken pinpoint of light, its warmth utterly meaningless against the scale of the world that is now consuming you. As you descend deeper into the thermosphere, the temperature paradoxically begins to soar. The few atoms that exist here are supercharged by solar radiation, reaching temperatures of over 700 degrees Celsius, or about 1300 degrees Fahrenheit. But you do not feel this heat. Temperature is the measure of how fast atoms are moving, but heat is the transfer of that energy. There are so few atoms here that almost none of them touch you. It's like being in an oven where the air has been removed. The elements are scorching hot, but you remain untouched. For now, this is the calm before the storm. You are still in the antechamber of the giant. The true atmosphere, the realm of clouds and pressure, is still hundreds of kilometers below, and you are racing toward it, a silent speck about to be swallowed by the storm. Your silent fall is about to end. After plummeting through hundreds of kilometers of near nothingness, you finally encounter the first true signs of an atmosphere. You've reached a pressure level of about 1/10 of Earth's sea level atmosphere. Here at the top of the troposphere, the part of the atmosphere where all weather happens, you enter the first cloud deck. This is the beginning of Jupiter's visible surface. These are not clouds of water vapor. You are plunging into a vast global layer of frozen ammonia ice crystals. The temperature here is a frigid minus 150 degrees Celsius, or minus 240 degrees Fahrenheit. The air, a thick mixture of hydrogen and helium, is finally dense enough to create friction. Your supersonic descent creates a shockwave, a cone of incandescent plasma that precedes you. For the first time, you would feel the planet fighting back. Air resistance begins to slow your fall, but the immense gravity still pulls you down with crushing force. The ammonia clouds are not white and fluffy. They are likely stained a dirty yellow and brown by unknown chemical compounds called chromophores, rising from the planet's deeper layers. Imagine flying through a planet-sized blizzard of fine yellowish dust. Visibility would be near zero. You are falling blind, tossed by winds that, even in this high layer, can reach speeds of 360 kilometers per hour, faster than the most powerful hurricanes on Earth. This entire cloud layer, stretching across the whole planet, is thought to be only about 50 kilometers or 30 miles thick. It's a razor-thin veneer on a world that is over 140,000 kilometers wide. It's like the skin on an apple, a delicate surface feature on a colossal body. As you punch through this layer, the ammonia snowstorm would give way to a brief, clear region. Below you, stretching down into the gloom, you would see the next layer of clouds, a darker, more ominous deck of brownish red. The pressure is building relentlessly. It is now equal to the air pressure on Earth. For a human, this would be the last even remotely survivable moment, a fleeting instant of familiar pressure amidst an utterly alien environment. But you are not stopping. Gravity is absolute. You continue to fall, leaving the ammonia skies behind and descending toward a region of even greater violence and deeper mystery. The hand of the giant is beginning to tighten its grip. As you fall deeper, you enter the realm of Jupiter's legendary weather. This is a world where storms are not events. They are permanent geological features. The planet's rapid rotation, a day on Jupiter lasts less than 10 hours, stretches its weather systems into colossal bands and jet streams that encircle the entire globe. You are now being swept up in winds that defy earthly comparison. Imagine being caught in a river of air moving at over 500 kilometers per hour or 300 miles per hour. This isn't a gust. It's a sustained, perpetual flow. The boundaries between these jet streams are scenes of unimaginable turbulence. Here, vast spinning vortices are born, some larger than entire continents on Earth. These are the white ovals and brown barges we see in photographs, cyclones and anticyclones that can persist for decades. You would be tossed around like a leaf in a hurricane, your descent becoming a chaotic spiral. And then you might see it, the Great Red Spot. It is not a storm. It is the storm, a high-pressure system so vast that it could swallow the Earth whole with room to spare. Its swirling crimson clouds tower kilometers above the surrounding decks. Its winds churn at over 600 kilometers per hour at the edges, while its center remains strangely calm. The eye of a hurricane larger than a world. For over 350 years, astronomers on Earth have watched this single storm rage. It is a weather system with the lifespan of an empire. What powers such a monster? Unlike on Earth, where storms are powered by heat from the sun, Jupiter's weather is driven from within. The planet radiates more than twice the heat it receives from the sun. This immense internal furnace creates powerful convection currents. Hot gas from the deep interior rises, cools, and then sinks back down, like water boiling in a pot the size of a planet. This vertical churning, combined with the planet's rapid spin, is the engine that drives its hyper-hurricanes and colossal jet streams. Falling into the Great Red Spot would be like descending into a planetary vortex. You would be pulled into a spiral, taking years to reach the center as you were carried around the storm's perimeter. The view would be a terrifying spectacle of crimson and scarlet clouds, a vortex of unimaginable scale and power. But even this, the most iconic storm in the solar system, is just a surface feature. The true violence of the planet is still waiting for you, deeper down, in the layers where the pressure builds and the lightning flashes. Leaving the ammonia clouds far above, you plunge into a deeper, darker region of the atmosphere. After falling through a relatively clear space, you would encounter the second, more substantial cloud layer. Scientists believe this deck is composed of crystals of ammonium hydrosulfide, a noxious, foul-smelling compound. The pressure here has now climbed to more than twice Earth's sea level pressure, and the temperature is a much warmer -70 degrees Celsius, or about -95 degrees Fahrenheit. The colors here would be deeper, shades of brown, red, and orange, as more of the mysterious chromophores from below well up and stain the clouds. But this layer is merely a prelude. Below it lies the most familiar, and perhaps the most violent of all Jupiter's cloud decks. It's a deep, thick, planet-spanning layer of water ice crystals, just like the cirrus clouds on Earth. To reach this layer, you have to descend to a depth where the pressure is 5 to 10 times that of Earth. Here, the temperature finally rises to a familiar 0 degrees Celsius, or 32 degrees Fahrenheit, the freezing point of water. This is a milestone of immense significance. Water is a much denser molecule than ammonia or hydrogen sulfide. This cloud layer is therefore thought to be the thickest and most dynamic of all. It is here, in this planet-sized thunderhead, that the true engine of Jupiter's storms is believed to operate. This is the planet's primary weather-making region. As you plunge deeper into this water cloud layer, the pressure and temperature continue to skyrocket. Soon you pass the point where water can exist as a solid or a liquid in the way we understand it. You enter a bizarre state of matter called a supercritical fluid. The pressure is now so high, over 200 times Earth's atmosphere, that the distinction between liquid and gas vanishes. The water is no longer in droplets or ice crystals. It is a thick, dense, hot fog that has the properties of both a liquid and a gas simultaneously. Imagine falling into an ocean that has no surface. The air around you simply gets thicker and thicker, gradually transitioning from a gas into a dense, soupy fluid without ever making a splash. This supercritical water is an excellent solvent, and it would be saturated with dissolved ammonia and other chemicals, creating a strange, corrosive planetary sea. You are no longer falling through air, you are sinking through a bottomless ocean of hot, high-pressure fog, and it is in this turbulent, supercritical sea that Jupiter unleashes its most terrifying power, lightning. Deep within the churning water clouds, an electrical storm of unimaginable proportions rages across the entire planet. This is the realm of Jupiter's lightning, and it is nothing like the lightning on Earth. The flashes we see in our own sky are powered by the friction of water ice crystals and thunderheads. On Jupiter, the same principle applies, but the scale is monstrous. The convection is more powerful, the clouds are deeper, and the electrical charges that build up are thousands of times greater. You are now falling through a perpetual twilight, illuminated by strobing, silent flashes of light. The lightning bolts here are not thin, spidery tendrils. They are colossal discharges, some 100 times more powerful than the largest superbolts on Earth. They are known as mega-lightning. A single bolt could stretch for hundreds of kilometers through the clouds and would appear as brilliant sheet-like flashes that could illuminate an area the size of a large country. Recent data from NASA's Juno spacecraft has revealed that lightning on Jupiter behaves in strange ways. On Earth, lightning is most common near the equator. On Jupiter, it's more common near the poles. Even more bizarrely, much of the lightning seems to originate from clouds containing a slushy mixture of water and ammonia. Scientists have theorized that this ammonia acts as a kind of antifreeze, allowing water to remain liquid at much colder temperatures than it should. This creates powerful slushy thunderstorms that generate what scientists have nicknamed shallow lightning in the upper atmosphere. But the true titans, the megalightning bolts, are thought to be born deeper down, in the heart of the water cloud layer. Here, the updrafts and downdrafts are so violent that they create immense charge separations. When the electrical potential becomes too great, the atmosphere breaks down and a bolt of lightning is unleashed, discharging terawatts of energy in a fraction of a second. Because the atmosphere is so dense, you wouldn't hear a sharp crack of thunder. Instead, the sound would be a deep planet-shaking boom, a shockwave that would feel less like a sound and more like a physical impact, a concussive blast propagating through the dense, soupy air. Your descent has become a journey through a planetary war zone. You are a microscopic speck, falling through a dark, high-pressure sea, battered by supersonic winds, and illuminated by city-sized flashes of lightning. The universe is putting on its most violent elemental show, and you have a front-row seat. The pressure continues to mount, and the clouds below are about to give way to the true, terrifying abyss of the planet's deep interior. You have survived the cloud decks, the ammonia, the hydrosulfide, and the titanic water ice thunderstorms are now far above you. You emerge from the base of the clouds into a new realm, the clear, deep atmosphere. There are no more clouds, no more storms in the conventional sense. There is only gas, pressure, and heat. The journey from here on down is a relentless descent into hell. The pressure is now over 100 times that of Earth at sea level, and it is climbing exponentially with every kilometer you fall. The analogy of an ocean is no longer sufficient. Imagine the pressure at the bottom of Earth's Mariana Trench, the deepest point in our oceans. Now multiply that by 1,000. That is the kind of pressure you are beginning to experience. The universe is squeezing you with a force that can alter the very nature of matter. The temperature is also rising at an astonishing rate. It has now surpassed 2,000 degrees Celsius, or about 3,600 degrees Fahrenheit. This is hotter than a blast furnace, hot enough to melt steel, tungsten, any substance known to man. But there is nothing to melt. You are surrounded only by a super hot, super pressurized gas of hydrogen and helium. This intense heat is not coming from the sun, which is now a forgotten memory hundreds of kilometers above. This is the planet's primordial heat, the energy left over from its violent formation 4.5 billion years ago. It is the heat generated by the Kelvin-Helmholtz mechanism, the process by which the planet slowly contracts under its own immense gravity. As it shrinks by just a few millimeters each year, that gravitational potential energy is converted into heat, which then radiates up from the core. You are falling toward the planet's engine. The gas around you is no longer behaving like a gas. It has been compressed to a density greater than that of water. You are sinking through a substance that is as dense as a liquid, but as hot as a star's atmosphere. The laws of physics as we experience them on Earth have broken down completely. Time itself would even be running slightly slower for you than for an observer in space, a real measurable effect of the planet's immense gravitational well, as predicted by Einstein's theory of relativity. You are falling through a transparent, glowing inferno. The gas itself, compressed to such an extent, would likely begin to glow with its own light, an eerie, deep red incandescence. Your world is now a featureless, luminous, high-pressure furnace, and you are still only a fraction of the way to the center. The greatest transformation, the most alien environment in the solar system, is still to come. The gas is about to become an ocean. As you sink deeper and deeper into the glowing, pressurized abyss, something profound begins to happen to the hydrogen that surrounds you. You are approaching a depth of about 13,000 kilometers, or 8,000 miles below the cloud tops. The pressure has now reached an almost unimaginable level, 2 million times the atmospheric pressure on Earth. The temperature is nearly 6,000 degrees Celsius, as hot as the surface of the sun. Under these titanic conditions, hydrogen is forced into a state of matter that blurs the line between liquid and gas forever. You have reached the liquid molecular hydrogen layer. There is no surface to this ocean. There is no splash. The transition is gradual, but absolute. The supercritical gas you have been falling through simply becomes denser and denser and denser and denser until it is indistinguishable from a true liquid. It's like falling into a fog that slowly thickens into water, then into honey, then into tar, without ever having a distinct boundary. You are now sinking through a planet-sized ocean of liquid hydrogen. The density of this liquid is still less than water, so in theory, an object made of rock or metal would continue to sink. The environment is utterly surreal. The liquid hydrogen would be transparent, but the immense heat and pressure would cause it to glow with a dull orange-red light, like looking into the heart of a cosmic ember. You are inside a self-luminous planetary-scale ocean. The forces at play here are difficult to comprehend. The weight of the thousands of kilometers of atmosphere above you is pressing down with a force of millions of pounds on every square inch. This pressure is so great that it is squeezing the hydrogen atoms themselves, forcing them closer together than they want to be. The energy stored in these compressed atomic bonds is immense. The flow of this ocean would be slow and majestic. Vast, continent-sized convection currents would dominate the circulation. Hotter, glowing liquid hydrogen from deeper within the planet would well up in slow-motion plumes, while cooler, denser liquid from above would sink back down in sluggish rivers. It is a lava lamp on a scale of thousands of kilometers, a slow, viscous dance of glowing liquid hydrogen that has been churning for billions of years. You are now truly in the belly of the beast. All the familiar concepts of our world, gas, liquid, solid, surface, sky, have lost their meaning. You are in a realm governed by the physics of the extreme, and yet the planet has an even more astonishing transformation in store. You are approaching the point where the pressure will become so great it will break the very bonds of the hydrogen atoms, stripping their electrons away and forging a new exotic state of matter, a metal made of the lightest element in the universe. The true hellscape is still below. Your journey has now taken you to a depth of over 20,000 kilometers, or about 12,000 miles. You are less than a third of the way to the planet's center, but you have reached the most violent and alien transition in the entire solar system. The pressure has now surpassed 3 million Earth atmospheres. The temperature is over 10,000 degrees Celsius. Here, the universe performs its most brutal act of alchemy. Under this cataclysmic pressure, the liquid molecular hydrogen you have been sinking through undergoes a phase transition. The pressure is so immense that it physically crushes the hydrogen molecules, breaking the covalent bonds that hold them together. The single electron orbiting each hydrogen nucleus is squeezed so hard that it is stripped away from its proton. The atoms themselves are broken. What's left is a sea of free-floating protons swimming in a chaotic swarm of delocalized electrons. This substance, a dense fluid of protons and free electrons, is no longer an insulator. The free-moving electrons can carry an electrical charge. The hydrogen has become a conductor. It has become a metal. You are now sinking through an ocean of liquid metallic hydrogen. This is not a metal like iron or gold. It is a silvery, reflective, mercury-like liquid, but one that is as hot as a star and under a pressure that can barely be replicated in our most advanced laboratories for a microsecond. The transition from molecular to metallic hydrogen would likely not be a smooth one. It might be a turbulent, chaotic boundary layer where storms of a different kind rage. Imagine vast, continent-sized thunderheads, not of water, but of molecular hydrogen, raining down droplets of metallic hydrogen into the layer below, or perhaps fountains of liquid metal erupting upwards into the molecular sea. These would be metal storms, a tempest not of weather but of matter itself, changing its fundamental state. Once you are in the metallic hydrogen ocean, the environment is defined by its electrical properties. The planet's slow convection currents are now churning a massive electrically conductive fluid. This motion is what generates Jupiter's colossal magnetic field, the largest and most powerful planetary magnetic field in the solar system, nearly 20,000 times stronger than Earth's. You are inside the dynamo itself. You are falling through a transparent, glowing inferno. The gas itself, compressed to such an extent, would likely begin to glow with its own light, an eerie, deep red incandescence. Your world is now a featureless, luminous, high-pressure furnace, and you are still only a fraction of the way to the center. The greatest transformation, the most alien environment in the solar system, is still to come. The gas is about to become an ocean. After a descent that has lasted for what feels like an eternity, through an ocean of glowing liquid metal, you approach the very heart of the giant. You are now over 60,000 kilometers, or more than 37,000 miles, below the cloud tops. This is the center of the planet's gravity, the point to which everything has been falling. For decades, our models of planet formation predicted a simple answer for what lies here: a solid core. The theory, known as core accretion, suggests that Jupiter began as a solid object, a primordial seed of rock and ice 10 to 15 times the mass of Earth. This massive seed then acted as a gravitational anchor, pulling in the immense envelope of hydrogen and helium gas that now makes up the bulk of the planet. In this model, that original core should still be there, a solid sphere of rock, metal, and exotic ices, crushed under the weight of 300 Earths worth of atmosphere. It would be a truly hellish object, with a temperature exceeding 20,000 degrees Celsius and a pressure of 50 to 100 million Earth atmospheres. A pressure so great it could crush diamonds into states of matter we can't even synthesize. But as your fall ends, you might not find a solid surface. Recent data from NASA's Juno spacecraft, by precisely mapping Jupiter's gravitational field, has painted a much stranger and more complex picture. The gravitational readings suggest there is no sharp, distinct boundary between the metallic hydrogen ocean and a solid core. There is no clear thud at the end of the fall. Instead, it seems the core is fuzzy. Imagine, as you sink through the liquid metal, it simply becomes thicker and soupier. It is gradually polluted with heavier elements, silicon, iron, carbon, and nitrogen, that have been dissolving and mixing with the hydrogen over billions of years. The core might be a vast, hazy region where heavy elements are diffused throughout the metallic hydrogen, a gradient of material that gets denser and denser toward the center without ever becoming truly solid. It's less of a pit inside a peach and more like the yolk of an egg that has been partially stirred into the white. What could cause such a fuzzy core? One leading theory is a colossal, ancient impact, perhaps in the violent youth of the solar system. A protoplanet the size of Earth, or even larger, slammed into the newly formed Jupiter. The impact would have been catastrophic, powerful enough to shatter the original solid core and dredge its heavy materials upwards, mixing them into the deep metallic hydrogen envelope. You are not arriving at a pristine original core, but at the scene of a multi-billion-year-old cosmic crime, the remnants of a collision that reshaped the very heart of the giant. The fall does not end with a landing. It ends in a slow final dissolution, as your vessel, crushed and vaporized, becomes just another collection of heavy elements to be stirred into the strange, fuzzy heart of Jupiter. While your journey into Jupiter ends in a furnace of metallic hydrogen, a fall into one of the other gas giants could offer an even more exotic fate. Let us shift our descent to the planet Saturn, Jupiter's smaller but no less majestic sibling. Saturn is colder than Jupiter, and its internal pressure ramps up more slowly. This subtle difference in temperature and pressure creates the conditions for one of the most spectacular phenomena in the entire solar system. diamond rain. The journey begins in Saturn's upper atmosphere. As on Jupiter, you would fall through layers of ammonia and ammonium hydrosulfide clouds. Deeper down, however, you encounter massive planet-spanning thunderstorms. The lightning in these storms is powerful enough to blast apart methane molecules, a common gas in Saturn's atmosphere. When a methane molecule is struck by lightning, it breaks apart, releasing its carbon atoms. These individual carbon atoms, now floating free in the dense hydrogen atmosphere, are like specks of soot or graphite. As they fall under the planet's powerful gravity, the pressure and temperature begin to build. The soot is compressed harder and harder. It is like the universe is applying the ultimate industrial pressure to these tiny carbon flakes. First, the carbon is squeezed into graphite. Then, as it sinks deeper to a depth of about 6,000 kilometers, the pressure reaches a critical point. The graphite crystallizes, it turns into solid diamond. You would be falling through a region of the atmosphere where it is literally raining diamonds. And these are not the small, polished gems we see on Earth. They could range from microscopic crystals to solid, uncut diamonds, the size of pebbles, or perhaps even boulders. Imagine a hailstorm where the hailstones are pure solid diamond, sinking slowly through the thick, soupy atmosphere. But their journey is not over. The diamonds continue to fall, sinking deeper into the planet for thousands of kilometers. As they approach the core, the pressure and temperature become even more extreme, beyond what even diamond can withstand. At a depth of around 30,000 kilometers, where the temperature is over 8,000 degrees Celsius, the diamond ocean awaits. Here, the pressure is so great that the solid diamond melts, forming a layer of liquid carbon. You would witness the final stage of the diamond rain, a planet-sized ocean of liquid diamond churning slowly above the planet's core. This incredible process is not unique to Saturn. The physics should be even more favorable inside the ice giants, Uranus and Neptune. These worlds are richer in methane and have the perfect pressure and temperature gradients in their mantles. It is almost certain that deep within these distant blue worlds, a constant glittering rain of solid diamonds is falling through their strange water-ammonia slush interiors. It is a process of natural planetary-scale gem-making, a reminder that the universe's treasures are forged in the most violent and unimaginable of crucibles. The Varney simulated fall is a journey of the imagination, guided by the laws of physics. But once humanity attempted this for real. On December 7th, 1995, after a 6-year journey from Earth, a small cone-shaped probe released by the Galileo spacecraft slammed into Jupiter's atmosphere. It was our first and only message in a bottle sent into the abyss of a gas giant. The Galileo probe was a marvel of engineering, a 34-kilogram capsule designed to survive the unsurvivable. It hit the top of the atmosphere at 47 kilometers per second. A speed so high that the atoms in front of it formed a shock wave hotter than the surface of the sun. An ablative heat shield, made of carbon phenolic, vaporized layer by layer, carrying away the intense heat and protecting the scientific instruments nestled inside. In just 2 minutes, the probe decelerated violently, experiencing a gravitational force of 230 Gs. Its mission was about to begin. After slowing down, it deployed a parachute and began its descent through the ammonia clouds. A journey that would last for 58 minutes. For that brief hour, it was our eyes, our ears, and our hands inside the giant. Its instruments measured temperature, pressure, wind speed, and the chemical composition of the atmosphere, beaming the data back to the orbiting mothership before it was lost forever. What it found was both expected and deeply puzzling. It confirmed the presence of the powerful winds and intense turbulence our models had predicted, but it also sent back a mystery. The probe found that the region of the atmosphere it had entered was incredibly dry, far drier than anyone had expected. The anticipated thick clouds of water ice were almost entirely absent. It was as if our probe, by sheer cosmic bad luck, had descended into one of Jupiter's rare hotspots, a dry, downwelling region of the atmosphere, a planetary desert. This finding sent planetary scientists back to the drawing board, forcing them to rethink how weather and circulation work on a gas giant. The probe continued to transmit as it fell. The pressure climbed from 1 Earth atmosphere to 22. The temperature soared to 153 degrees Celsius, hot enough to boil water. All the while, the immense weight of Jupiter's atmosphere was crushing the probe from all sides. Finally, after descending about 156 kilometers below the cloud tops, the signal stopped. The probe, Its heat shield gone, its parachute likely melted, was vaporized and crushed into its constituent atoms by the immense pressure and heat. Its brief, heroic plunge was over. It had survived for less than an hour, but the data it sent back has shaped our understanding of gas giants for decades. A final, faint whisper from inside the storm. For more than 20 years, the data from the Galileo probe was our last direct contact with Jupiter's deep atmosphere. Our models were refined, but the fundamental mysteries, the missing water, the structure of the core, the true nature of the storms, remained. Then, in 2016, a new explorer arrived. The Juno spacecraft, a spinning, solar-powered probe, entered into a long, looping polar orbit around Jupiter, designed to fly closer to the planet than any mission before it. Juno was not designed to fall in, but to peer through the clouds using a suite of powerful instruments. Its mission to map the giant's magnetic and gravitational fields, and in doing so, to finally reveal what lies beneath. Juno's discoveries have been revolutionary, turning much of what we thought we knew on its head. Its gravity science instrument confirmed the perplexing nature of Jupiter's core, revealing it to be fuzzy and diluted, spread out over nearly half the planet's radius. This discovery sent shockwaves through the community of planetary scientists, suggesting a far more violent and chaotic formation history than the standard core accretion model could easily explain. Juno's microwave radiometer, an instrument that can peer deep below the visible cloud tops, has given us our first three-dimensional view of Jupiter's weather. It revealed that the iconic bands and zones are not just skin-deep phenomena. They extend thousands of kilometers down into the atmosphere, far deeper than anyone had predicted. The Great Red Spot is not just a surface storm. It is a colossal vortex with roots that plunge at least 500 kilometers into the planet. Furthermore, Juno solved the mystery of Galileo's missing water. By mapping the atmosphere across the entire planet, Juno found that the water is there, but its distribution is highly uneven. The equatorial regions are indeed surprisingly dry, just as Galileo had observed, but the polar regions are rich in water. This suggests that the dynamics of Jupiter's atmosphere are far more complex than a simple boiling pot, with different circulation patterns dominating different latitudes. Perhaps most beautifully, Juno's camera has given us an entirely new perspective on the planet. By flying over the poles, it has shown us a Jupiter we have never seen before, a chaotic swirling canvas of deep blue, dotted with continent-sized cyclones, arranged in stunning geometric patterns. It is a view that is more like a piece of psychedelic art than the striped planet we are used to. These revelations from Juno are like echoes from the abyss, data points sent back from the edge of the impossible, each one giving us a clearer picture of the beautiful, violent, and deeply strange nature of the largest planet in our solar system. Our fall has come to an end. We have journeyed from the edge of space, through clouds of ammonia and water, and into a glowing inferno of supercritical gas. We have witnessed storms the size of worlds, lightning bolts of unimaginable power, and a bizarre rain of diamonds. We have sunk through an ocean of glowing liquid hydrogen and finally reached the planet's enigmatic heart, a place where the distinction between a core and the atmosphere dissolves into a fuzzy, mysterious soup. This impossible journey reveals a profound truth about our solar system. The gas giants are not just scaled-up versions of Earth. They are fundamentally different kinds of places, governed by a physics so extreme it forces matter itself into exotic states we can barely comprehend. They are less like planets and more like failed stars, their immense gravity and internal heat creating environments that are closer to a stellar furnace than to the rocky worlds we know. They are the architects and the bullies of the solar system. Their immense gravity sculpted the orbits of all the other planets, and their chaotic youth likely exiled countless smaller worlds into the interstellar darkness. They are both creators and destroyers, their existence essential for the shape of the solar system we see today. And yet, for all that we have learned from missions like Galileo and Juno, they remain worlds of profound mystery. What are the chromophores that paint their clouds in such beautiful colors? How deep do their storms truly go? What is the ultimate nature of their cores? And what does it tell us about the violent birth of our entire planetary system? The fall into a gas giant is a journey to the limits of our knowledge, a stark reminder of how much we have yet to explore. They are a testament to the fact that our universe is not obligated to make sense to us, and its greatest wonders are often hidden in the most inhospitable and unreachable of places. The giants wait, guarding their secrets in the deep, silent darkness of the outer solar system.